Hello and welcome to the third video tutorial on RF circuit design using Qucs. In the first two videos, I have talked about the getting started or the basic guide of Qucs, and in the second video, it was basically to show how to set up an S parameter simulation in Qucs. In that example, I used a basic ideal transmission line which is available in Qucs library to show how to set up an S parameter simulation and what are the results that we get after the simulation and how to display them in the by using various display templates that are available in Quicks. Let's move on to a little bit one step further. I would say it's still not an advanced tutorial, but it's again we will be setting a basic S parameter simulation, but this time we will be doing S parameter simulation for a microstrip line. So let's go ahead and create a new project. New, I'll call this as S para of microstrip microstrip line, and this is my project 3. Okay, so you have the project and you know the project flow in this, so save the schematic as para of microstrip line, which is project 3. Okay, so we have the schematic saved. Let's quickly go and place the microstrip line here. We go to transmission lines and we have different components. This is the microstrip line, and okay, we have the microstrip line here. Press escape to exit out of this, which is the pretty standard thing in Quicks. Okay, so we have microstrip line which is named as ms1, and we have three options here which are visible to us. First is substrate. Subst stands for substrate, which is equals to substrate 1. But what does this mean? Let's look at it a little bit later, but we have two other options, which is width of the transmission line and length of the the microstrip line. If you have studied basic microstrip line theory or microwave theory, in which you have seen a microstrip line is type of a transmission line which is fabricated on a substrate, and it has a definitive width which determines its characteristic impedance, and that is why we have the most common options here, which is the substrate and the width and length of the transmission line, uh, which means that in order to define this microstrip line, we also need to define the substrate. Let's go ahead and check. We have the substrate block here. I just click and place it here, and you see we have a couple of options in the substrate. Now, depending upon what substrate you choose, your microstrip line is going to have a different impedance depending upon the width. Let's look at what options we have here on the screen for the substrate block, and you see by default it's named as substrate 1, which means that this microstrip line is going to use this substrate model in order to do the simulation. And we have a couple of options here. First is name of the substrate, which is substrate 1. Okay, that is fine. It has to be same because this microstrip line will understand that this microstrip line ms1 is fabricated on this type of substrate. Next is the ER, which is the dielectric constant of your substrate, or the relative permittivity, which is currently at 9.8. H stands for height of the substrate or thickness of the substrate, which will again determine the impedance, the characteristic impedance of the microstrip line. Currently it's set at 1 mm. T is the thickness of the metal, which is copper, and 35 micrometer is okay, pretty standard. And tan D, this is another important parameter. Tan D stands for loss tangent, which is the important parameter for the substrate. So in this simulation, oh, by the way, in case if you don't know what these stands, you can always double click on the block, and now you see ER stands for relative permittivity, which is same as dielectric constant. H stands for the thickness of the substrate in meters, it says, but if you put mm, it will automatically take it as mm. T is thickness of metallization, tan D is loss tangents, and we don't need the other values. So let's go ahead and set this microstrip line on an FR4 substrate. So because that's the most commonly used substrate, it's low cost. substrate and widely available, easily available. uh, the values that I'm taking for FR4, I mean, they can vary a lot. It varies from maybe 4.2 to 4.8, the relative permittivity. But I'll take the values from CST Microwave Studio because I have used CST a lot, and by default, the FR4 model which is available in CST Microwave, it uses these values. It uses the relative permittivity as 4.3, and click on apply. Otherwise, it won't change the value. Height, the standard height which you get for FR4, most commonly used is 1.6 mm, but you have other heights as well. It depends on your simulation, what you are going to use for your final fabricated prototype, maybe. Yeah. So 1.6, I'll click on apply. T is fine, and tan D. Again, this value I'm taking from CST Microwave Studio. It uses loss tangent as 0.025. I click on apply. Okay. So we have the substrate defined, which is FR4. If you want, you can even change the name as FR4. Okay, let's do that for our better understanding, so that whenever if I share this file with someone, he understands what kind of a substrate it is. So I just named it FR4. If you are using maybe like Rogers or any other substrate, you need to go to its datasheet, and you will find all these values there: the dielectric constant and the loss tangent, and obviously the height. Okay, so I named it as FR4, but you need to change it here as well, because this model, the microstrip line, will look for a substrate named as substrate 1, and we don't have any substrate named as substrate 1 on my schematic. So let's go ahead, double click on it, and you see the substrate. My substrate is FR4. Oh, FR4. Okay, apply. Width is 1 mm, length is 10 mm, and we don't need the other options. Okay, so now I set this as FR4. Let's go ahead and try setting up the S parameter simulation. I won't change the width as of now because I'll show you how to do that, how to calculate the width for a given impedance using Qucs. Yeah, we don't need any other tools, so we don't need to Google it or something. Uh, we'll select the sources. As I said, for S parameter, you need power sources. You can check my previous video, how to set up the S parameter simulation and why do we need power ports and all other basics. So I'll just connect the power sources to the microstrip line using the wire, and I will use the reference ground. Okay, it's all set. In my previous video, as I used the ideal model of a transmission line. Now microstrip line is also a type of transmission line. It is a transmission line, but it is fabricated on a substrate. It's etched on a substrate, and it has various properties, like it has losses attached to it, because we will have some kind of fringing fields coming out of the transmission line. We will have some dielectric loss because of the loss tangent of a dielectric. If it's more lossy, you are going to have more attenuation in the signal traveling through the this kind of a microstrip line. But for now, let's go ahead and set up the same simulation as we did before. So we kind of made a matched system. We match the entire impedance of the system 50-50-50. So let's go ahead and do that. Again, if you have studied basic microwave engineering or microwave theory, we know that the guiding component, once the substrate is obviously set, the guiding parameter for the characteristic impedance of a microstrip line is the width of the microstrip line. In this case, it's width option here, and if I go back and just for comparison, if I place the transmission line, you see here we directly have the impedance, because this is a general model of a transmission line. It doesn't talk what kind of a transmission line it is. Maybe it's a microstrip line, or it's a strip line, or it's a grounded coplanar waveguide. Doesn't matter, you just define the impedance, that's it, because it just it uses the model of the transmission line. Just delete it. Okay, but here it's a specific type of transmission line, which is the microstrip line, and here the width will guide the impedance of this microstrip line. So for the first type of simulation, I want this to be 50 ohms. So how to calculate the width? Obviously, you can Google the formula, or you can Google calculators for like impedance calculation of microstrip line. But we have a tool here. You go to tools, you go to line calculation, and we have a nice tool which pops up here, inbuilt into Quicks, which is very nice because it's quite handy. So first thing is you need to select the type of transmission line that you want to model. And we have couple of things here. We have coaxial lines, waveguides, CPWs, and microstrip line, obviously. So I'll just go to microstrip line, and you can see also see a small picture here, what parameter refers to which dimension in the small photo here. And the substrate parameters it automatically took, I guess, from what I have defined, but let's just cross check it. This is permeability, and we don't play around with permeability, at least for these kind of circuits. Okay, so ER is 4.3, height is 1.6 mm. uh, T is the copper or metal thickness, okay, let it be. And height, okay, maybe I need to change this because this is in mils. I'll make it to mm, and mm is 1.6 mm. And tan D 0.025, which is okay. Frequency, let's keep it 1 gigahertz. And okay, we are getting something here as values are inconsistent. We'll check that, it doesn't matter. Then yeah, here we have to put what's the impedance that you are looking for. There are two things here. You can see there are two options, analyze and synthesis. So either what you can do, you can change the width here. I am not playing with the length currently because length will only control the phase of the transmission line, and I'm not interested in that as of now. I just want to look at the impedance, which is governed by the width of the transmission line, this W. So I'll change it to maybe like 2.5 mm, and I'll click on analyze. As soon as I click on analyze, okay, now it says values are consistent because I think it automatically took care of these difference in units in the calculation. But yeah, so as soon as I click on synthesize, for these values you see the calculated results. ER effective is the effective dielectric constant, which we don't need to look into now, maybe later in some advanced things. And there are various things like conductor loss, dielectric loss, okay, good, but we don't need it. What we need to look at is the Z naught, which is the characteristic impedance. So for 2.5, the characteristic impedance of this microstrip line for these kind of for this width and on this kind of a substrate is 62 ohms, but I said I want 50 ohms. So what I can do is I can keep on changing the width until I reach 50 ohms, or I can simply put 50 here and click on synthesize. As soon as I clicked on synthesize, I have some values here which changed, which is uh, it's somewhat incorrect because from my calculations I remember it should be around 3 mm for 50 ohm on 1.6 mm thick FR4 of 4.3. So I think there is something wrong here. Okay, I think this HT is causing a HT and H. Okay, I think there's something wrong here. What is HT? Doesn't say. Doesn't matter. We will. What I'll do is I'll quit this and maybe open it again. Tools, line calculation. HT is. Mhm. Okay, I'm not sure what HT is, but okay, let's go and maybe we have something here. We don't have anything. Okay, doesn't matter. We'll go to line calculation and we'll keep it as low as possible. So maybe like 1.6 mil is good enough because, or maybe zero point 0.1 mil. Okay, but H, as you can see from here, H is the thickness of substrate, which is 1.6. ER is 4.3 and tan D is 0.025. This is what matters. And again, I'll keep this 50 ohm synthesize. Okay, this seems something to be not correct. Okay, it's height of the top box, which it's taking into consideration for the calculation. Okay, now it's good. So basically, the way this runs is it's it basically is going to solve some equations, and you need to define the box for it, like in which it should do this calculations. Box is like, maybe you can imagine it's sort of a boundary condition, but we don't need to change it as far as I have used this, but maybe I accidentally changed it while changing something else. But yeah, you can put it as 1 centimeter. It's some sort of a boundary condition for solving this equation. And this is pretty correct because I remember this. So if I click on again synthesize 50 ohms, the width is 3.1 mm. Okay, let's go and check if it's correct. I'll close this. I'll change the width to 3.1 mm, which I got from the calculator, and we are good to go. Let me just check. Okay, 3.1 mm. Okay, high length I'm not changing right now because, as I said, it will change the phase of the transmission, and I don't want to look into that for now. Uh, let's go ahead and put our S parameter block, go to simulations, S parameters, and let's run it for 1 to 6 gigahertz, and I'll reduce the points. 50 points is good enough for our calculation. Okay, let's go ahead and run the simulation. Okay, no error as of so far. Cartesian. We missed one thing again. If you remember from the last video, if I run this, okay, let's go and check. I won't be having dB values. Okay, there are no dB values. So let's go back and change it to dB. Use the equation dbs11, and I'll use the dB inbuilt function. Convert the S11, which is calculated already in Qucs. Okay, I won't be putting all the equations. S11 is fine. And let's go ahead, select, double click on S11, apply. Okay, and okay, nice, we have some good looking curve here. Let me drag it, and yeah, so we have the dbs11 values versus frequency. Let's go ahead and change the limits. I don't like the way it displays by default. Okay, 1 to 6, and we have rather a sharp point here, so let's go back and increase the number of points so that we have a much finer graph. Let's go and make it 101, resimulate, and yeah, now we have a much smoother curve here because we increase the number of points, so it increases the number of calculations. At each frequency point it will calculate dbs11, and we have a nice looking curve here, and we have pretty good matching at this frequency. Okay, so this is dbs11 versus frequency for a microstrip line. If you want to read the values, again select the marker, just place it anywhere on the graph and you can change it. You just select it and use your arrow keys to move it at various frequency points, and you see, since it's a matched system, like I said, it's for 50 ohms. I designed it for 50 ohms, and you see the S11 or the input return loss is pretty good. It's basically all the time under minus 40 or 45 dB, which is a good value for this transmission line. But if you want to check the impedance, let's say, I mean, how do you know it's 50? Okay, matching is good. Then we know the method. You plot the Smith chart, you click the Smith chart, and in Smith chart we always select the linear values, apply OK, and we have something, but it's not visible, so maybe I'll try zooming in again, and because the number of points are less and the frequency sweep is smaller, you don't see it. Maybe we change the limits of y-axis. 1 2 2. Oops, start is at mm, oh no, I think I should let's not play around with Smith chart much. I'll look into it later, but we can just, yeah, okay, this is good. We can put the marker on it. Okay, so currently we are at 1 gigahertz. Select the marker, and 1 gigahertz is close to 50 ohm, and the reactive part is also pretty small. We'll just use the arrow keys again to change the frequency points. Let's go at 2 gigahertz. 1 gigahertz is okay. Okay, this is 2 gigahertz, and we are again around 50 ohms. Okay, but we see at some frequency where we had a better matching. What was that frequency? Maybe I'll just put it here, and that frequency is 4.25 gigahertz, where we have a pretty good value for S11, which is minus 82.6. So let's move to that frequency, 4.25. Just use the arrow keys to navigate or to move the pointer, and oh, oops, I missed. Yeah, okay, so you see at 4.25 I have a perfect 50 ohm here, which is at the center here, and 50 plus J reactive part is almost 0. and only the real value is there, which is equals to 50, which, okay, that's why we have a dip in the S11. Let's go ahead and make some changes again. As I said that this is what the width controls the impedance of the transmission line. So okay, let's play with it a little bit. We can maybe make it half, around 1.5, resimulate, and the results are already changed. You see, it's poor now because yet at 4.25 it's minus 8.89 dB S11, and you see it's like for most of the frequencies beyond 3 gigahertz it's not matched, and the same can be seen from the Smith chart. So we have some good looking Smith chart now, because the point basically in the first simulation, the transmission line was 50 ohm, sorry, the microstrip line was 50 ohm, so the point was always here, and that's why we couldn't see the curve properly. But now we can see the curve pretty nicely on the Smith chart. And you see currently the impedance is almost double of the previous. It was 50, currently it's 106 at the same frequency. And you see how it is not matched at any point, because it's just rotating. It's not there at the center where is the matching point. So I think that's it for this tutorial. In this tutorial we saw how to define a microstrip line in Quicks, and how to run the S parameter simulation for this microstrip line, how to design the microstrip line by using the inbuilt calculator for synthesizing the transmission line, either for the getting the proper impedance, or by using the width and checking what the impedance will be of the transmission line. And obviously we also looked at how to define the substrate and what are the different parameters of the substrate, and we also looked into the data display part of it on Smith chart and the Cartesian plot. So that's it for this tutorial. Thank you and see you next time.